Hi guys, this is our second problem on refrigeration, and this time we have a heat pump. It also uses 134A. This heat pump is used to get a space at a constant temperature of 25 degrees Celsius. So this is the, the need for this heat pump was to warm up. So this is the value, the heat that we value, QH, we may say. It must absorb heat from somewhere, so it does from geothermal water that enters at 50 degrees and leaves at 40. That there's a temperature decrease of 10 degrees, and the mass flow rate of that water is 6.065 kilograms per second, or 6.5 grams per second. The refrigerant, we are being told that it enters at 20 degrees with a quality of 23% to the evaporator and leaves at the inlet pressure as saturated vapor. That's what the way the evaporator leaves, the refrigerant leaves the evaporator. But between the evaporator and the compressor, there is a heat loss of 300 watts to the surrounding. Once that we have the pressure, when we go into the compressor, it compresses to 1.4 megapascal at the same temperature as the inlet, the same entropy. We are asked to determine the degrees of subcooling in the refrigerant in the condenser, the mass flow rate of refrigerant, the heating load on the COP for the heat pump, and we are going to ignore the T because paragraph D, because that is a second law analysis, or exegy, that we are starting next class. So, how do we solve this problem? First, we're gonna make a diagram, and we're gonna change colors this time. We're gonna, so we make sure that when you see the solution, it looks different. This air condenser, our compressor, our evaporator, and our expansion valve. So we would like to keep the ambient of a room at 25 degrees, and we have some water that enters at 50 degrees and drops at 40 with a mass flow rate of water, right? So that will make heat flowing QH, QL, and we also know that this point, quality is 0.23, that means 20%, and temperature is 20 degrees. We know that here we have a quality of 1, and that we are losing some heat and we have an exit pressure of 1.4 megapascal. When we are looking for, is the degrees of subcooling, the mass flow rate of refrigerant, the heating load, and the COP. So we will have this as state 1, state 2, state 3, state 4, and there one point that is already fixed. State 4 is fixed, so once that we know H4, we know that H4 is equal to H3, and we only need to compare that H3 with HF at 1.4 megapascal to define temperature at 3. With that we can get the subcooling, or not if we have no subcooling. As for the refrigerant flow rate, we know that the heat that is absorbed by the evaporator is the same heat that is released by the geothermal water. So that heat of water should be the same as the heat that the evaporator absorbs. So this is the mass flow rate of water times specific heat of the water times the temperature decrease this time. And this should be the same as the mass flow rate of refrigerant times H1 minus H4. So solving, and this is very similar, solving for mass flow rate of the refrigerant, we have that is the mass flow rate of water times the specific heats of water times the temperature difference divided by H1 minus H4, and that will take care of the mass flow rate of water. We already have a way to identify if this temperature is what we need to, if we have subcool or not. So I know to get the QH will be the mass flow rate of refrigerant times H2 minus H3, and remember that this comes from first law analysis. We already did it in the video for ideal cycle. And finally we need the COP. So COP is what we value in this case is QH, because we are using it to compute, to warm up this ambient divided by what I need to give. Okay, and how do we get this? Will be mass flow rate by H2, and I will say 1H as a H inlet, because this H inlet is different from this H, and we have been told that we have a heat loss of 300 watts. So let's do a first law analysis. For the connecting pipe. We have done this in class. So for the connecting pipe, we know that we have Q in minus Q out plus work in minus work out plus the mass flow rate of refrigerant times H in, that is H1, minus H out, we call H in. Let me change these names so we avoid confusions. We're going to call this HX. So I'm going to erase here HX. So, and also here. So we avoid confusions between H in being H out, Hx. So for this analysis we notice that we don't have any Q in, we don't have work in or work out since it's just pipe, and I forgot the second term, which is the change of energy with respect of time. And we know that this number is also 0. So at the end, we can solve for Hx. And Hx will be H1 minus Q out divided by the mass flow rate of refrigerant, and you are asked to get this expression starting from this. A more formal analysis will require that we consider this Q and getting a temperature of the boundary to compute the new entropy. Since we don't have information of the temperature at which this heat is being transferred, we're going to assume that S1 is equal to Sx, and this is an assumption. It's a big assumption, because since we are losing heat, we are reducing the entropy in this in the fluid. Okay, so basically what we need to find out is each of the enthalpies, and for that we're going to use our tables, and let's start by saying that state 4, which is already fixed, H4 equals HF plus X4 HFG at 140 kilopascal. So you are asked to compute this H4 is equal to 121.24 kilojoules per kilogram, and we know that this is equal to H3. State 1 is also fixed. Since we have 140 kilopascal, we have been told that we should neglect all pressure drops, and X1 equals to 1. It's saturated vapor. From this, in our tables, we get H1 261.59 and S1 is equal to 0.9234. This is kilojoules per kilogram, this is kilojoules per kilogram Kelvin. Now, state X, which is just prior to the compressor, we said it was Hx equals H1 minus Q leak divided by the mass flow rate of refrigerant, And once to solve this, we need to get for the mass flow rate of refrigerant. So the mass flow rate of refrigerant, just by substituting, we have 0.065 times 4.186, which is the specific heat of water, times 10 degrees temperature drop, divided by H1 minus H4. This is 261.59 minus 121.24. This mass flow rate is 0.019039 kilograms per second. So by substituting these values, we have Hx to be equal to 210 kilojoules per kilogram. Now for the compressor state 2, we would like to find out with pressure equal to 1400 kilopascal and S2 equal to S1, which is 0.9234 kilojoules per kilogram Kelvin. By interpolation, we have H2 equals 280.36. We already know H3 because H3 equals H4, which is 121.24 kilojoules per kilogram. Now we're going to compare H3 with HF at 1400. At 1400 kilopascal. Since H3 is less than HF, we know that it is subcooled. So we know it's subcooled, and what we're going to look is looking at a temperature table. We find out that the temperature 3 should be between 52 and 48 degrees. So interpolating with enthalpy, we know that temperature 3 is 48.8. Now the subcooling will be the saturation temperature at 1400 minus temperature 3, and this is 3.6 degrees. That's our subcooling. Mass rate that we get here, 0.0139 kilograms per second. Let's mark it. And by substitution, you can get QH by substituting H2 minus H3. And this will give us 3.08 kilopascal. So QH 3.08 kilowatts. Sorry, not kilopascal. Kilopascal is not a unit of energy, it's a unit of pressure. So this is kilowatt, this power. Finally, should be, we said it was QH divided work in, and by substituting different H's, we should have 2.26. Please do all the math and see that you have the same results. Okay, thank you. Last problem will follow.